So the last thing that I want to do together today is both to kind of, again, summarize what the various versions of Stokes' theorem can actually tell us, but also along the way sort of get another win in the process of discovering kind of a shortcut, a whole class of integrals whose values we can be assured of without having to do any calculation, which is always a good idea when we can get away with it. So what could I be talking about? Well, here's the touchstone that we'll start with. So remember when we were talking about circulation and path integrals a while back, and part of the work that we did there was we decided that, you know, if we have a simple closed curve, then Green's theorem can help us convert this circulation integral into a double integral. If my vector field is a gradient of some scalar potential function, then we also have another theorem available, the fundamental theorem. Because the integral is path independent, we just had to find that potential by using the ungradient process, and then take the difference of that potential at the endpoint minus the starting point. But there was something special that happened if both of these situations were true. If I have a gradient vector field, and also I have a simple closed curve as the curve that I'm trying to find the circulation on, then these two things combine to tell me that the circulation is zero. In this case, because the ending point and the starting point of my path would be the same point, so that when I do this, I get the same number minus itself, and that gives me an answer of zero. So the place we want to go next to sort of wrap things up, so I want to kind of ask the analogous question of, let's suppose that I have a flux integral, and my flux integral is an integral on a closed surface, but also I happen to know that my vector field that I'm integrating is the curl of something. We would call that something also a potential function for that vector field, except it would be called a vector potential, because in order to turn it into an actual scalar function, to turn it into a vector field, we would take the vector curl of it. So if f is equal to the curl of something, and I also have a closed surface, then maybe we can say something special. Similarly, on the line integral side of things, in the three-dimensional case, it should work just the same as in the two-dimensional case, that if f is a gradient vector field, and I also have a closed curve, then I should be able to have the same result in 3 dimensions as I had in 2 dimensions. But what I want to do here is I want to see both of these instances, both the case of a circulation integral of a gradient vector field on a closed curve, and also the case of a flux integral of a vector field that has a vector potential, so it's the curl of something, on a closed surface. I want to see these as both examples of the same phenomenon that's happening. And to do that, we're going to apply Stokes' theorem to the first case and the divergence theorem to the second case to see what it is that we end up getting. Stokes' theorem applied to my line integral of a gradient vector field on a closed curve would tell me that what I can really replace this line integral with is a surface integral of the curl of my vector field. But my vector field is the gradient of something. It's the gradient of h. So I get the curl of the gradient of h becomes the integrand for this surface integral. Similarly, if I apply the divergence theorem to this case, the surface integral, the flux integral of a vector field which is the curl of something on a closed surface, then divergence theorem tells me that the integrand for this triple integral is going to be the divergence of the curl of b. b here is this thing that we take the curl of to get my vector field f. And so the last activity for the day is going to ask you to compute these integrands. So tell me, what does the curl of the gradient of h actually look like with respect to the partial derivatives of the function h? And then what does the divergence of the curl of b look like with respect to the second derivatives of the component functions that make up the vector field b? So here's the last act that I have for us to work on together today, is to just compute those out. Compute this, what I call a second derivative, the curl of the gradient of h, and also compute the second derivative divergence of the curl of b in terms of the partial derivatives of b and h, right? And just sort of see what happens. And to make this work, we're going to assume that h and b are functions that have continuous second-order partial derivatives. So this is also going to give us our first instance of practicing taking the curl of a vector field, which is nothing more than taking this derivative operator and taking its vector cross product with whatever I'm crossing it with. So order of operations, work your way from the inside out, find what the gradient of h looks like using the partial derivatives of h, and then take the curl of that thing and see what happens. When I take the curl of the gradient of a function h that has continuous second-order partial derivatives, the first component in that curl is the y partial derivative of the z partial derivative of h, so hzy, minus the opposite, minus hyz. Right? That's the first component. The second component ends up being the z derivative of the x derivative, so h xz minus the x partial derivative of the z component of the z partial derivative, so hzx. And the third component is hyx minus hxy. So that when I do out that curl, what I get is something that looks like this. But what's going to happen here if I have hzy minus hyz? It's the zy partial derivative minus the yz partial derivative. What's that going to give me if h has continuous second order partial derivatives?
It's the same. So
they're the same.
0.
And so I get 0. And the same thing happens in the second entry, hxz minus hzx, 0. The third entry, hyx minus hxy, 0. And so when I do the curl of the gradient of something, as long as that something has components which have continuous second order partial derivatives, Clairaut's theorem of equality of mixed partials tells us that those mixed partial derivatives are equal to one another, and so when I subtract them, they vanish. So what this is kind of telling me is that for any scalar function h with continuous second order partial derivatives, we have that the curl of the gradient of h is just equal to the 0 vector. So that's kind of nice. In particular, the reason that that's nice is that it fills in the lower left-hand corner of this diagram. That if I have a line integral where that line integral is being taken on a closed path, right? So we have this side is an option, so that's what brings Stokes' theorem into the picture. But also, if my function happens to be equal to the gradient of something, then Stokes' theorem tells me that that circulation is just going to equal the surface integral of the curl of the gradient of h. But the curl of the gradient of h, we just said, was equal to 0. And so then that surface integral ends up being equal to 0. So that curl of the gradient is equal to 0. It's like the best of all possible worlds. But this just gives me 0. So I get 0 if I integrate a gradient vector field around a closed curve, because Stokes' theorem tells us that that integral is just equal to the surface integral of the curl of the gradient. And the curl of the gradient of any scalar function with continuous second order partial derivatives is just equal to 0 on the nose. It's not just that the integral is 0, but the whole integrand is equal to 0. And if we were to go through and do the same combination of derivatives for the divergence of the curl of b, we would find out that the same thing ends up happening. We would do a lot more calculation, but the same thing would end up happening, that the divergence of the curl of b is also equal to the scalar function 0. So for any vector field b with continuous second order partial derivatives, we have that the divergence of the curl of b is equal to scalar function 0. And so that fills in the lower right-hand corner of this same diagram. Right? That if I am finding a flux integral on a closed surface, and also my vector field is the curl of some vector potential function, then I'm once again in the best of all worlds, because this integrand is just going to be equal to 0. And if the integrand is equal to 0, then the integral is going to be equal to 0. So any vector field which is the curl of some vector potential, if I integrate it on a closed surface, its surface integral is going to be equal to 0, according to the divergence theorem, for the same reason that when I integrate for circulation of a gradient vector field on a closed path is also 0, by the same application of these Stokes theorems. And so that's nice because it also kind of underlines the unity of all of these different results. They're all kind of telling us analogous things, just in different context of line integrals versus flux integrals, and triple integrals versus double integrals versus the single integral that we get from the ordinary fundamental theorem of calculus-looking result for path-independent vector fields.